a relay. It'll go very quickly if I stop. Maureen, you want to introduce today's speaker?
I'm just going to come to the front and yell. So, hi everyone, welcome to the colloquium today. Today our colloquium speaker is Dr. Craig Hadley, who is currently the Winship Distinguished Research Professor and Director of Undergraduate Studies in the Department of Anthropology at Emory University. Craig completed his PhD at the University of California, Davis, and he is best known for his research in the areas of global health, demography, and nutritional adaptation in Africa and beyond. His most recent work has focused on engaging and testing universal models of anthropometrics, body shape, and child health, about which this work he'll be speaking to us today. His talk is entitled Exploring Competing Ideas About the Relationship Between Body Shape and Health. Please join me in welcoming Craig Hadley.
Hi everybody, thanks for having me up and chatting with me, and thanks to Dawn for arranging my trip too, and Morgan for inviting me. This is great. I was at the Pop Center at Brown University for 2 years, and it was like really the most intellectually engaging 2 years of my academic career. I loved it. It was fantastic. So I'm happy to be back at a Pop Center for a while. So I'm going to talk today about some work that my colleague Dan Hrushka and I have been doing. Dan's at Arizona State University. He's a really brilliant guy that we've been doing over the past 4 or 5 years. And for neither of us, it's not our primary area of research. Mostly I study food insecurity and poverty in Ethiopia and Tanzania, and this is just sort of something I wanted to do on the side when because I couldn't get to the field. But what Dan and I have been doing over the past couple of years is thinking about the relationship between human body shape and human health. And what's motivated this is what many of us probably do in our studies, which is at some point you put people on a scale and put them up against a stadiometer and get their height and come up with some metric of weight for height, probably the most famous of which is BMI, weight over height squared. And we use this very simple ratio as some measure of health and well-being. And typically what we do, certainly in anthropology, this is, almost every human biologist or biological anthropologist would do this in their studies. You put somebody on these scales, and then we apply these universal cutoffs based on the weight and height. So for instance, in the BMI, the standard would be, if their BMI is above 25, then we might say that that person is at risk of overweight or obesity, or we might say the prevalence of overweight and obesity in a population is whatever. And for studies looking at children, this is all changing as the obesity epidemic goes global. But for a long time in global health, right, for kids, we often use Z-scores, and we would often use the -2 standard cutoff. And if the child's weight for height falls below that, or height for age, we'd make some assessment about whether they're at risk for undernutrition, etc. Now, these approaches are sort of universal. We apply them indiscriminately. Doesn't matter where the child came from or the adult came from. We tend to apply the same cutoff. And we're not the first to critique this idea of body mass index. This is an idea that seems to be constantly critiqued. And the critiques around whether we should use these universal cutoffs kind of fall along two lines. So one branch of critiques have focused on whether the relationship between between body mass index and adiposity, whether that relationship is the same across different racial and ethnic groups, with some finding that there's some different relationships across different racial and ethnic groups. And a second body of critiques have tried to look at whether the BMI mortality relationship is the same across different regions or racial and ethnic groups. And so the key area studies here have been those from South Asian populations, showing that mortality seems to increase at a lower BMI than among European groups. Now, you could look at this body of work in two different ways. And so one group of people probably looks at that and says, yes, there are differences across racial and ethnic groups in geographic areas, but they're very small and we don't need to think about them. We probably don't need to change the cutoffs. And I guess if you're an anthropologist and your bread and butter is human variation, you look at that and say, oh, there's differences there. There's something to look at. And what we're seeing right now is just the tip of the iceberg. Let's go out and explore global human variation. And so this is what has motivated in part what Dan and I have been doing, is starting to see really is to to use an anthropological term, to problematize the body mass index and weight for height ratios and look more broadly. And we begin our investigation of this building on a couple of observations. And one is that it is clear that body shape responds to resources. These are data from roughly 1 million women from the demographic and health surveys, plotted along household wealth. And it's unambiguous that women in wealthier households have a higher BMI. So body shape is clearly responding to energy, whether that be excess energy or insufficient energy. But the second observation that we build on is one that comes from anthropology and human biology, and indeed naturalists and other observers for a long time have noted that there do seem to be differences across populations in their body shape, and those differences don't immediately seem to be due to access to resources. And if you open up any Intro to Biological Anthropology textbook, you would see some examples of this, and the classic examples would be contrasting those living in the high latitudes who have short, stocky builds, and contrasting that maybe with folks who are living right near the equator, like the newer, who have these long, slender phenotypes. So we have clearly that body shape is responding to resources, but there might also be these well-established population differences. And those population differences seem to extend back some time. Archaeologists have known about this for a while. These are data from Chris Ruff showing in skeletal samples looking at bi-iliac breadth, which is sort of how wide your pelvis is, and looking at skeletal samples across, as you move away from the equator, showing that bodies get stockier as you move further away. And these hard sample results are mirrored in soft tissue. These are differences in body composition across different populations. And the way you would read this is comparing, matching, in this case, a Pacific Islander with, let's say, a white US male, and matching them on fat mass, and then looking to see what the BMI would be of that Pacific Islander. And so if you match a Pacific Islander with a white US male on fat mass, the BMI of the Pacific Islander is about 4 units higher. So there are these really large differences when we match on the thing that BMI ostensibly tells us about, which is potentially fat mass. So we have these large population level differences. So what Dan and I have been trying to do then is to say, what we've been thinking about is that when we have a measure of BMI, that it's potentially telling us about a couple of different things. Partly it's telling us about well-established population differences in body shape, and potentially about the impact of living in an energy positive or energy negative environment. So when we have this measure, it might be telling us about multiple things. And our current understanding of lots of diseases and ill health is that it should really only be the impact of living in an energy positive or energy negative environment that's associated with poor human health. We don't really think that some of this other variation should actually be linked with health outcomes. And this should be just as true for children. We've primarily looked at kids living in environments with insufficient energy. And then again, it should only be the portion of child's weight for height that's due to insufficient energy that should be driving health outcomes, not potentially the other part. So, we sort of think about this as a two-compartment model of BMI. And thinking about BMI in this way challenges common uses of BMI. So the standard use of BMI or weight for height ratios is to assume what we think of as an invariant or a universal model, which is that there might be some population distribution, say, of weight for height, and that as children or adults, or say children fall off that, as their disease scores go down, their risk of morbidity and mortality goes up. Or we might think about this as BMI. As BMI goes up, they increase in risk of morbidity and mortality. But everyone's falling off of the same curve. But if we think that there might be population differences in BMI, then instead we might get a model that looks like this, where there's lots of different curves. So, and this sets up an interesting contrast in predictions, because let's say if we take a child from this blue population and their weight for age z-score is say -2, if the correct reference is their population weight for height, then their risk of morbidity and mortality might be quite low. But if the correct population reference is this universal, then it should be quite high. So there's this contrasting prediction here. So with that theory and motivating observations in mind, what we've set out to try to do is to take this idea and apply it. And we've sort of set out in a series of questions that we've kind of walked through over the last couple of years. And the first question is, can we decompose adult BMI into these two compartments? That is, can we take adult BMI and look at what fraction of BMI is due to resources and what fraction is due to underlying variation in body shape? And then if we can do that for adults, can we apply the same analysis to kids? And if we can do that, then can we begin to explore whether these two pieces of BMI have different causes? What accounts for the variation? And then finally, and this is sort of the stage we're at now, can we ask if those different components predict population health in different ways? Are they giving us the same information? Okay. So how do we decompose population BMI into these two pieces? Now, ideally what you'd want to do is to go get a global sample, put people in, let's say, a DEXA machine and get lean and fat mass from a big sample of different ethno-linguistic groups. And that's challenging for a variety of reasons, as you can imagine. So what we try to do instead is to sit in the comfort of your own desk and use a statistical approach to estimating these two components. And we begin this by defining this concept of the basal BMI. And we define the basal BMI as a measure of the BMI of a population which has not yet experienced the nutrition transition. This is the global transformation in diets with more energy, greater diversity, etc. And so that's the basal BMI is our attempt to sort of reflect the part of the BMI that's due to well-established population differences in body shape. It's probably telling us something about lean mass. All right, and the way we do this then is a statistical approach in which we calculate the expected BMI of, first we use all women, and this is simply a data constraint. The data sets we use are primarily female. Then we estimate the BMI of someone who's 19 to 24 years of age. And we do this because, at least for a part of the lifespan, adiposity is increasing. And so we try to get people who have attained their maximum height, but they haven't started yet accumulating fat mass. And we further select on individuals who are breastfeeding, which again is negatively associated with fat mass. We get those individuals who have low or no education, living in a rural setting, and in extreme poverty. Each of these is negatively associated with fat mass, so essentially what we're trying to do is to strip away as much fat as possible. Yeah?
Is being pregnant possibly associated?
We exclude all pregnant women, I'm sorry.
Okay, but
Yeah.
breastfeeding women have been pregnant.
They have been, but their breastfeeding is still negatively associated with fat mass. Yeah.
How to do the experiment.
Yeah, I guess we could select on, yeah. And so what we're doing is slowly, in a sense, chipping away and trying to get the BMI of someone who has the least fat on them. And to do this, we select on people who have a wealth of $400, 2005 purchasing parity, and below. So these are very poor individuals. And if you've worked with the DHS data, you know they don't have an absolute wealth measure. So we had to develop a measure so we can use this. We can compare all DHS data sets on a common wealth metric. Okay. So we do this approach and we apply it to the demographic and health survey data, which have their, there's warts in these data sets, like all data sets, but they are a tremendous resource for exploring human variation in body shape. So we apply it to 60-ish countries in the demographic and health survey. And what I'll do now is to walk through, over the past couple of years, some of the key findings we have from this approach of trying to estimate these two compartments. All right. So when we apply our algorithm to the demographic and health survey data, we get results that look like this. And let me just walk you through one of these bars and show you what they are. The gray bar here, here's Jordan, and the gray bar is our estimate of the basal component of BMI. And the white bar, or the entire bar, is the average BMI among women in Jordan. And so the white piece here is indicative of what we might call residual BMI or excess BMI. That's the BMI that's above and beyond their basal component. And you can see there's tremendous variation across places. Here's India, very low BMI overall, as we all know, and a very low basal component and a large excess component here. The number here is the sample, so we have to reduce the sample down once we start selecting on all these individuals. So for Jordan, you can see there's only 27 women in that sample, and that's because Jordan is doing what is in a fairly good situation. It's developing and the income is going up. So when we try to select on people who are extremely poor, we get very few of them. So we can't apply this technique to, say, the United States because people aren't poor enough in the US samples. But in many places, unfortunately, that's not a problem. Bangladesh, for instance, there's 2,500 women who we can estimate basal BMI off of, etc.
How did you define it? In these countries have not yet started the nutrition transition?
Yeah.
What was the selection
criteria
here?
Yeah, for these countries, what's the selection criteria? They're low to middle income, low and low middle income countries. We have to have, normally we go for more than 30 people meet our criteria. So Jordan's in here, it's 27, so. Yeah. Once, there's no, Albania, for instance, there's a DHS for Albania, but nobody's poor enough in the country to fit our criteria here. Yeah.
So this walk measure is really critical. I don't know if you want to elaborate now or maybe wait for the end to elaborate on how you construct the walk.
Do you mind if I wait till the end? Because
No.
I don't want to put people to sleep too early, and if you don't work with the DHS, it might not be that interesting. So when
One of the questions you have, you pointed to the gray and the white, but there's two other things in between. By the way.
Yeah, so this is the air around our estimate of basal BMI. Yeah. And there's none here because this is just the prevalence or the average BMI in a population. Yeah. Okay. So we find that there's this tremendous variation across countries in both, or actually all three of the components, in BMI, in basal BMI, and in residual BMI. So you can see, for instance, again, Jordan has a very high total BMI, of which a large fraction is made up of residual. And you could contrast that. Here's Democratic Republic of Congo, which actually has very little residual BMI and very high basal BMI. And then India, it's very low BMI, but a large fraction of it is excess. We'll talk about that case in just a second here. So we see this tremendous variation in both of these components. And we see that when we do it for children as well. For kids, at the country level, there's about a 1 unit difference in basal weight for height across countries. And in sub-Saharan Africa, we can look at specifically at ethno-linguistic groups, and there's about a 1.5 unit difference in weight for height, basal weight for height. And you can contrast that with the variation in weight for height z-scores due to wealth across the DHS, which is somewhere about 0.7 to 0.5 among kids. So there's a substantial fraction of the weight for height that's appears to be due to something other than access to resources. And one of the things that's interesting is that when we estimate the basal BMI for adults and the basal BMI for children in the same countries, that they're very strongly correlated with one another. So if you know something about the maternal basal BMI, it tells you something about the children's basal BMI or weight for height as well. And that's interesting because it suggests that whatever is driving the population level differences in adults is doing that before the kids are 5 years of age. And so that radically constrains the hypotheses we would propose for what accounts for adult BMI. For instance, it's probably not adult physical activity, which has been a common hypothesis, but whatever it is, it's got to be doing that work before the kids are 5 years of age. So we have a technique now for decomposing adult BMI and kids BMI, and that then allows us to begin to explore what maybe are some causes of these different variation. of the differences between populations. And one thing is, if we look here, this is country level GDP against the basal component for roughly 60 countries. Each data point here is a country. This is the basal BMI, and there's no association between basal BMI and GDP. When we look at excess, that's the white bars on those graphs, that's strongly correlated with country level GDP. So what's driving the gray variation back in this slide here doesn't seem to have anything to do with wealth, but what's driving this has to do with wealth. And that's the same for kids. This is the basal over here with no association, and this is the residual. Another way we've looked at this is to look at some ecogeographic correlates of BMI and basal BMI. For biologists and human biologists and biological anthropologists, there's sort of a long tradition of looking at these what are called ecogeographic rules that predict body shape. And so this well-known idea, as I said at the beginning, that it's called Bergman's rule, which is that if you live in a colder climate, bodies tend to be stockier, and if you live in a warm climate, bodies tend to be long and linear, dissipate heat. And so for our samples, we looked at whether heat is driving any of this. And here we have the warmest monthly temperature in each country. And that's predicting negatively the basal component for kids and also for adults. But the prevalence of GDP or the prevalence of food insecurity in a country doesn't predict the basal component here. And we look at the excess component. The temperature doesn't predict the excess, but our measure of resources predicts the excess component here. So these seem to be driven by different factors, the different components here of basal weight per height. Now, we had been very interested in exploring what drives the basal component, and going into this, our strong hypothesis was what's driving the dark gray bars, or the basal component across populations. Our hypothesis was that that would be linked to pathogen prevalence. And the basic idea here is one taken from life history theory, which is that it's really expensive to run your immune system. And if you're being bombarded by, if you're living in a very dense disease ecology, you should upregulate your immune system, and that should come at the expense of lean mass, which is expensive. And so what we thought we would find is that what explains variation in basal BMI across populations is something having to do with the disease ecology. Now, what we need to test this are good measures really of historical disease, because you want to know something about long periods of selective pressure. It's very hard to get those data. So we identified a few measures of historical pathogen loads and ran those against basal body shape for kids and adults, and there's no association there whatsoever. And it's not clear to me yet whether that's a data problem, where there are these historians who reconstruct disease burden across populations, and those maybe aren't the best measures to use. So it's not clear to me whether we don't find a disease predictor there because of the data or because there's really nothing there. And what we find is that for kids, there's a small effect of contemporary temperature and a very large effect of adult body shape. And then we find that adult body shape is strongly associated with temperature. So this is the maximum temperature, and this is the basal BMI. And here, instead of the country, we've gone down a level and used the ethno-linguistic group. So within any country now, we have multiple. So for instance, the Iraq and the Maasai, those are from Tanzania, another Tanzanian group. There's a bunch of Kenyan groups. There's a bunch of, here's the Gujarat down here, the newer. So we've broken it down a further level. And we see that there's this temperature gradient suggesting that some of the variation in basal BMI, not the excess part, but the basal part, is due to temperature effects. And this got us thinking then about sort of deeper patterns and deeper migration histories in genetic ancestry and what's driving contemporary body build. So contemporary body build seems to have some impact from contemporary temperature. But when we've been working with these data, one of the things we kept noticing is that there's clear regional clustering. So Swaziland, Lesotho, Zimbabwe have positive very high basal BMIs. Our samples from the Americas have very high positive BMIs. Chad, Ethiopia, et cetera, have fairly low basal BMIs. And what's interesting is that we know that there was a historic migration down the coast, the east coast of Africa into southern Africa by folks who are somewhat genetically similar. There's also, we find some evidence across the middle of sub-Saharan Africa of a kind of a path of basal BMI that looks very similar. So that made us wonder whether there's a deeper link here. And then what we're picking up is that there's maybe some population structure to this BMI, to the basal component here. And what we, essentially what we wanted to know is if two individuals came from the same, or shared some ancestry, is their basal BMI going to be more similar? Or is contemporary temperature really driving the show here? All right, so it is difficult, right? So as soon as you step into this genetics, you actually think you should have some genetic data. But of course, we're working with demographic and health survey data, which doesn't have genetic data. So in 2008 or 9, Sarah Tishkoff published a paper in which they used a very large sample and estimated these 14 clusters, ancestry clusters. And then in an appendix or supplementary material for a number of contemporary ethno-linguistic groups, they have a table that shows for each of these ethno-linguistic groups what percent ancestry those group is from these 14 clusters that they estimated. So we took the demographic and health surveys, which ask questions about language and in some cases ethnicity, and we know geography, and we were able to link up the individuals in the demographic and health surveys with their ethno-linguistic, with our best guess of what their ethno-linguistic group was. And then we can put on the percent ancestry from these 14 clusters for these groups. And essentially what we want to know is if two individuals are the same ancestry, and one's living in a warm climate and one's in a cold climate, is the basal BMI going to look similar between the two or different? So we use these ancestry clusters to essentially look and see how well they predict basal BMI. And what this table here is showing you is for 74 ethno-linguistic groups for which we could get these data for, we can match them up. It's showing the R-square for a model in which we're predicting basal BMI for women based on maximum temperature. The average temperature or the minimum temperature, these don't really seem to do that much. And then when we put up in these ancestry variables, what happens to the R-square? And you can see the R-square goes up considerably. And we do a mediation analysis that shows that almost the entire effect of temperature drops out or is mediated by genetic ancestry. And what that looks like then, or allows us to do, is to use our model then to say what would the basal BMI of somebody look like if there were 100% ancestry of one of these different groups. And so here I think here's a Native American. If someone was not that anybody is one of these things, but 100% Native American ancestry, their basal BMI would be 2 units higher. So you'd want to essentially adjust for that. Yeah.
But isn't temperature totally correlated with ancestry? I mean, how do you decompose those from each other? I mean, that's like, look at me, my ancestors are from Scotland. I get sunburned easily.
Yeah.
But I mean, these things are totally wrapped up with each other.
They, in some sense that they are, but I think we know from, at least in sub-Saharan Africa, these population histories that there are these really pronounced migrations, which would divorce ancestry.
And you have enough variation in that to truly divorce the temperature from the ancestry?
I'm going to say yes, but I can, yeah.
I mean, that would seem to be necessary for your identification.
Yeah, I mean, if you plot, so one of the ways you could do is to plot, for instance, ancestry by some, like latitude, for instance, and if you're right, then we just see this clump, and if otherwise. So that would be a 5-minute task and really interesting to look at. I'll do that and get back to you. Yeah, as an anthropologist, I would say we have enough variation because people are moving all around, but that's totally just because I'm an anthropologist and I feel like we have to say that. So yeah, but skin color would be a really good analog to this. You think we know populations are living in areas that have darker skin than you would predict, and vice versa, and that's because of past migration away from high UV areas. Yeah.
Right. So
yeah.
the current temperature is irrelevant, but it's what happened to your ancestors
exactly
1,000 years ago.
Yes, and that's I think what we're picking up. Yeah. So if we do this. Is essentially using our model to say what would the basal BMI of the basal BMI be if you're 100% one of these ancestries. Yeah. Okay. So we feel like we can. We're not totally 100% confident in this, but we have a technique to decompose kids and adults' BMI. We have some sense that what's driving these is potentially current temperature, but there seems to be a deeper signature here of population structure. And then we can ask, if it even matters, what are the population health consequences of thinking about the world in this two-compartment model? And we need to do a better job for the adults for this. The DHS data for adults doesn't have, across studies, doesn't have the greatest health information for very comparable health information for adults. But one of the things we've tried to do is to look at the basal BMI and the excess BMI against diabetes prevalence at the country level, adjusting for age. And there's no association with the basal component here. We see a stronger correlation with the excess component here, which is just what we would expect. And for the kids, we can do something similar. And so again, what we have here, each of these dots is a country. And we've estimated the basal BMI for each country and the residual BMI. It's essentially that bar chart I showed at the very beginning. But in the DHS data, in most of the DHS data sets, the primary female caregiver is asked whether each child or many of the younger children have had in the past 2 weeks a fever, a cough, or diarrhea. And so we can use those to get an estimate of the prevalence of child illness. And we might say that those are self-reported data, so they're not very good. But the Tanzanian DHS actually collected C-reactive protein as well, which is a good measure of that the immune system is upregulated. And when we use those data, we see this perfect dose-response relationship between the number of symptoms reported by the mother and the child's C-reactive protein. So suggesting that it's not perfect, but it's, some kids are missed, but it suggests that the female caretakers are onto something when they say the child has been sick. And that's been replicated in a number of different non-DHS studies as well. Anyways, when we do that at the country level, again, so each of these dots is a country. This is the reported prevalence in that country's DHS by the residual BMI weight for height. And what we see is as children or countries' kids accumulate excess weight for height, the reporting of illness goes down, and there's no relationship here with the basal component. And because the DHS data for the kids are at the individual level, we can go a step further. And we can estimate a model in which we're predicting whether the child was reported as ill or not, whether they scored yes to any one of those three. And we can look at household wealth, and it's negative, so wealthier households are likely to have healthier kids. This is not news from the front. But we can also put into that model the basal weight for height at the country level, and each individual child's deviation from their country's weight for height, basal weight for height. And what we see here is the basal component is not associated, not significantly associated with illness, but each child's deviation from their country's basal weight for height is associated, and it's negative. And that then has interesting implications for the invariant or the universal model versus the ecological multi-model. That result suggests that this picture of multiple populations is a better fit to the data. Because we find that where a kid's population basal weight for height doesn't predict their ill health. What matters is their deviation from their individual population's weight for height. And we're working on trying to do the same thing for adults here, but I don't have any results yet. Okay, so I'm going to start to wrap up here, and then should be done by 12:45. Okay, so I think our data suggests that this ecological model is potentially a better fit to the data. And what all of this suggests to us is that when we put somebody on a scale, as many of us do in our studies every day, that measure is telling us not just about resource availability and adipose tissue, but potentially about deeper population structure, potentially about contemporary ecogeographical variables, and by that we just mean how hot it is or how cold it is. And that potentially there's some neutral variation across populations as well. Anthropologists are really interested in this neutral variation right now because there was a study. There's a long history in biological anthropology. This is like a boring aside, sorry. There's a long history in biological anthropology looking at pelvis, and there's been a lot of theorizing that the pelvis has very little variation across in populations because it's so critical for walking efficiency, and that there should be selection really shaping this. And yet it turns out when you look at populations across the world that there's tremendous neutral variation in pelvis. It just seems like there's a lot of different ways to make a pelvis that's about the same in terms of efficiency. And so it may be true also for some bodies that the ratio of lean mass to body mass, some of the lean mass may be neutral. I don't know, we're looking into some models to look at that. And what's neat about this, I think, is that our results, which come from come from sort of sitting down and running some regression models, actually are converging with results coming from archaeology. And archaeologists have a long history of being interested in and have noticed population differences in robusticity. And the common hypothesis for some time was that populations differ in their body shape because they engage in different amounts of physical activity. And there's this idea known as Wolff's law, which is that bodies and bones respond to physical activity and get larger. And that was a common explanation for why some populations just looked larger than others. And then in 2010, Libby Cowgill, who's an archaeologist in Missouri, said, well, if that's true, then when we look at the infants and children from these populations, they should all look pretty much the same because they haven't had any time to engage in physical activity. So she collected a really interesting sample that included adults and infants at about 1 year of age. These are skeletal archaeological samples. And what she showed is that even in the skeletal samples of the 1-year-olds, they predicted and were very, very highly associated with the robusticity of the adults in those populations. And so what she argued is that yes, there may be differences in physical activity between populations that drive differences, but she says it's hard to argue that this alone could be responsible for producing population differences before the age of 1. So she has a very different take on why we get these differences in robusticity across populations. It's also, I think, interesting and maybe promising that our approach also identifies those classic examples in biological anthropology textbooks. So if you open one of those, what you're going to see is a picture of the Nuer as very thin, and Native Americans and Arctic populations is quite stocky. And when we look at our ancestry markers here, this would be a Nuer, estimated as having very, very low basal BMI, and this is a Native American population, very high. So we can, the individuals that we identify as being quite slender or not slender are exactly the ones that anthropological textbooks use as case studies. So it would have been problematic, I think, if we didn't find those. So. Our technique also identifies what is sort of emerging in some of the public health nutrition work of this fat-thin phenotype in South Asian populations. So here's a quote from Shaikh et al. Saying, their findings, which is of an anthropometric study, suggest that Bangladeshi women exhibit excess adipose tissue at substantially lower BMI compared with non-South Asian populations. And the basic idea here is essentially that some South Asian and populations have a low BMI, not because they're lacking fat, but because they're lacking lean mass. And that's exactly what our statistical approach identifies. So in the India case, we get a very low BMI, but a large fraction of it is probably fat mass, and very low levels of lean mass, and same with the Bangladeshi population. So our approach uncovers what other people have uncovered through a very different approach. This suggests, if there's anything to this, it suggests we need to be cautious about using BMI in and of itself to make population level comparisons. And it also potentially resolves what's sometimes known as the India paradox, which is pointed out here by Dres and Deaton, which says undernutrition levels in India remain higher than for most countries in sub-Saharan Africa, even though those countries are much poorer, have higher levels of mortality, etc. So a number of people pointed this out, using measures of weight for height and BMI to say, well, India is doing well, but the BMI is really low. Other places in Africa are not doing well, but the BMI is high. And that is only a paradox if you use the entire BMI. That disappears entirely if you use the residual. So here's Democratic Republic of Congo, which I think we can all agree is a country in Africa that has high mortality and not doing very well. And so what some people have said is the paradox is that the BMI of India is lower than the BMI of Democratic Republic of Congo. But if you use the residual component here, there's no paradox anymore. It's exactly what you would expect. And so we may be, if we make comparisons just using BMI across populations, we may be making false inferences. Okay. And that suggests, too, that when we look globally, that we might want to account for the component of children's weight for height and of adult BMI that's due to the basal component and the residual component. When we look across different regions, countries, and subdistricts to see what fraction of the variation in BMI, observed BMI and observed weight for height is due to basal BMI and basal weight for height, we find fairly substantial numbers here, which suggests that a lot of the variation we're seeing out there is potentially not due to excess or insufficient resources, but due to this underlying component here. And we can use this then to maybe monitor the risks of different of overweight and underweight in a more precise way. So we've used our method here to use country basal BMI to adjust the BMI and then adjust the number of people who are at risk. And so when we do that, we get some interesting findings. So here what we've done is taken the universal standard, which would be a cutoff of a BMI of 25, and say here's what East Timor, for instance, the prevalence of overweight and obesity would be using the standard model. When we adjust for their basal BMI, the risk goes up quite a bit. And you can do that for others. Here's India. It goes up obviously quite a bit because the basal BMI is so low. Same with Bangladesh and Yemen. I don't have a picture, but we can do the same thing for children's weight for height. And when we do that, we identify West Africa, which by standard measures of weight for height, seems like those children are doing relatively well. But when we adjust for their basal weight for height, it looks like the nutritional status is potentially much worse in West Africa. And the same for the Americas too. So we might expect we find higher levels of, let's say, chronic diseases than we would expect given the BMI in those particular areas or the weight for height. So, and some of those have been puzzles for some folks, and so it potentially unlocks those. All right. So let me just conclude, I think, with this slide, which is that and this is a slide from a paper in 1987 critiquing BMI, so this is not a new thing. And I like it because it's in part by an anthropologist, Bill Leonard, who said there's a finite limit to what we can accomplish with weight and length alone, however these two variables are juggled or put into regression equation. And I think Dan and I have hit the limit of juggling these and putting them into regression equations. I think there's a clear road forward that we need to do, which is to get some people sample them strategically from, we know certain places we think the basal BMI is very low. We should selectively sample folks from those populations and get them into a DEXA machine, and we can begin to validate our approach here. So that's sort of a next step for us. But there's some questions and a lot of uncertainty. We've been thinking a lot more about how weight for height and BMI, how that impacts on monitoring. So I've showed you some of our thinking on this. Our other steps are to think if we can get child mortality data broken down by diseases that should respond to residual weight and diseases that shouldn't, we should find that the basal BMI is not predictive of some mortality, but is predictive of other sources of mortality. It's also not entirely clear what the correct scale is here. And by that I mean, do we say, for instance, here is a cutoff for Ghana, or let's say Tanzania, or is the better reference to say here is a cutoff or a curve for the Maasai in Tanzania? That is, really, is the country the right level or the ethno-linguistic group? You know, if you know, actually, if you probably know anything about the world, right? That ethno-linguistic groups don't really typically, they're not stopped by borders. Think about southern Ethiopia and northern Kenya. These ethno-linguistic groups are flowing across these, and so it seems arbitrary just to put a line between those. It's not entirely sure what the right is. Okay, so the other thing I've been thinking a lot about is how to best estimate the basal component for kids. For adults, it's very easy because they've reached their height and they're kind of done growing in some ways. But kids, if you've ever plotted, for instance, a kid's BMI curve across infancy into childhood, they're growing, and it's our estimates of the kids' basal weight for height are probably not as reliable as they are for adults, and that's something that's another one of our next steps, is to look at how stable these are. When we look at multiple DHS surveys across countries, what you should expect is if we took the 1995 Ethiopia DHS and the 2015 Ethiopia DHS, our estimate of the basal BMI should be the same if there's long history to that. And those estimates are incredibly reliable. In fact, the survey year falls out of a statistical model when you're seeing if survey year predicts basal BMI at the country level, it falls out. We need to do the same thing for kids. We haven't done that. And then the fun thing, of course, is to think about where these come from and what's their adaptive value, if any. Why do we see this variation in basal BMI? Our hunch going into this was it was going to be a really cool story about the history of pathogens, and that didn't pan out at all. And so we might be able to get better data, or there might be something else going on. So I would welcome your thoughts on that, and I will. Thank you. Thank you.
Let me start by saying that I don't have any problems with the theoretical implication. But women in South Asia, age 15 to 24, still have higher mortality rates than men, and this does not happen anywhere across most places across the world. In 1 to 4 they have high mortality, and 15 to 24 they have high mortality. So it's partly a question to you that how much of your variation so you're taking that basal BMI, to the extent that we think that this is basal BMI, how much of that variation is driven by particularly low status of women in South Asia? And then the second aspect is about this prevalence of disease. Now, I mean, there's evidence that people with higher SES report more diseases. Diarrhea and disease across the world have been going down, but over time the prevalence of these diseases has gone up. So then in the DHS surveys, so then basically when you do this comparison within the survey, you're basically comparing it within what the country's standard is. So people are reporting according to what other people what they consider disease things. So yeah.
So the first question is that the mortality of Indian women 18 to 24 is higher than men. Yeah. What's the mortality? What are the causes of mortality?
We don't know that at all.
Oh, okay. I mean, I guess what we would say, I mean, from this perspective, it would say essentially that's probably mortality that's not due to energy availability. These women have particularly low status, and that's partly why what has been the explanation in the literature of why they have such low BMI. Yeah.
Now your basal component is restricted to that component, right, of South Asia. So maybe it makes sense to look at some other ages.
Yeah. Or other places in the world that have also women with very low status, and see what's, is this a low status India or something else going on? Yeah. And sorry, I don't know if I caught your second question.
The prevalence of disease estimates in the DHS, they've been going up over time. Richer people report more disease than poorer people across countries.
Yeah, okay.
So I'm just thinking that when you use that to say that you're taking this supports a country level BMI, they're just reporting it based on what they think is disease, so that would support a country level BMI.
Oh, okay, yeah, okay. So when we use adult prevalence of diabetes to look at the adult basal BMI, whether it predicts, it's not coming from them, it's coming from national level reports on, so that, and it's a smaller sample because it's not self-report data. And for the kids, so what you're saying is that why would that vary systematically with the deviation? Because they're getting richer. So that means, so then you're saying essentially if we selected among a comparably low group, if we just took countries along the bottom income bracket, that you might not find this, because you're saying that what's happening is GDP is driving reporting.
Idea than the
I mean, it would be good if we had, for instance, C-reactive from a bunch of studies, so you could see whether you're systematically deviating from that. Which we have, I think that was, that's. I have to think about how we can test whether that's actually a problem in the DHS, but it's a really good point. I appreciate it. Yeah, thanks. Yeah. No, go for it, and then we'll go back behind you.
Since the United States, at least to this point, is a diverse society, the implication would seem to be that an appropriate prescription from the medical community would be to find the excess BMI by population group and have different criteria, presuming it correlated with, and that would then be, I guess, a stronger, you would have to provide a much stronger critique against these BMI, since that would be an impossible task.
Yeah. This is why you don't work in I don't work in the United States. It gets too. One implication would be that there may be added information from knowing the basal BMI from the country where someone is coming from. Yeah. Yeah.
Then they would have to establish criteria.
Exactly. Yeah. And I think I'd want to get people in a DEXA machine before you get to that step to do some more. But I think this gives us reason to potentially say it's worth looking to see whether estimates of basal BMI are stable across populations and look at immigrant groups here and to see in the United States if immigrants from different countries with different basal BMIs are at different risk of chronic diseases here. I think that would be an interesting study which might then lead to that. Yeah.
Hi, thank you for your talk. I wanted to ask a few questions about the social components, which may be behind some of the variation you're talking about, because you talked a lot about ecogeographic and other things.
Yeah.
So, and maybe I don't fully understand your measure, but my understanding is this basal BMI measure that you're using is like, you're basically using within a country or ethnic group, the like poorest women as kind of a reference
Yeah.
group. So I wonder if what you're measuring is really like a BMI inequality or something about the variance. Like, for example, you're comparing like India and the DRC. And so kind of building off what Ashish said, so some of what you're seeing is like this large component of the like residual and like the low basal, which is kind of showing some inequality that there's that the poor women are very low, but that there's kind of like a lot of variation in the population. But is it possible that that basal could also be reflective of generations of deprivation of nutritional resources? So for example, comparing the DRC and India, in India you have the poorest groups have for, thousands of years been deprived of nutritional and other forms of resources, which may have led to different body shapes. Whereas in the DRC, where you have like tribal society where resources are more distributed equally, that could lead to like a higher lower bound on your basal BMI. So I was wondering how much you think those kind of within society social factors may be playing a role here.
Yeah, I think that's a great question. And my hunch is that there's something to that.
Okay.
The data would suggest there isn't something to that, because what we've done is we've tried to sort of pick and choose comparably really poor places with long histories that are not, and because people often will pull out India, like what's going on with India, but there are other places it would be hard to argue that they have not had really long periods of extreme deprivation, and we see very different levels of basal BMI. We also see that the correlation between the women's basal BMI and the men's is very similar. In fact, there's only one place where we find at the country level a very big difference, and that's in Swaziland, and that's probably because there's massive male out migration that we're not picking. The DHS, the men aren't there in the DHS to get measured. So, and if you use standard measures of women's power and autonomy as whatever they are in the DHS, they don't predict basal component at all, which it doesn't get at the history part there, but it still seems like there should be something there. So part of me thinks, I think there's something there. Every way we tried to look at that, there hasn't been, but that's probably because we haven't been smart enough to find the right way to look at it. So do you have any suggestions?
No, I guess my concern is that like if these variance in the basal is the result of things like social deprivation, then do we naturalize that by allowing for different measures across different cultures?
Yeah, which I think is it's a really good question. Yeah.
In the United States, wouldn't you have to invert your algorithm? So you'd have to select on people being wealthier and so forth, because think about obesity here.
Yeah.
If you're poor, you're not, deprived of food.
Yeah.
But quality food and
Yeah.
calorie dense diets. So I mean, think about the most overweight states, West Virginia.
Yeah.
So it seemed like you'd have to
Georgia.
run it the other way.
Yeah. There's almost no way we can cut this to get the people to fall into the sample from the United States, because even when which is an interesting story about poverty, but in absolute poverty, but nobody would fall into the sample, and even if you flipped it, they're on such a different scale. Yeah, you can't, like rural Ethiopia versus Mississippi. I mean, yeah, they all have their issues, but absolute poverty is not even close. That's my take on it. So yeah.
So the BMI combines height and weight, which from my limited understanding of thought is driven by very different processes. The height being kind of early childhood condition and weight being much more short term. And you focused on BMI, which convolutes that all into one
Yes.
measure. And I was wondering, can you just tell the same story? If you had to pick one of the two, which one would map onto your story? Or anyway, how does that?
Yeah. Okay. Well, let me skirt that question by saying a problem for us is that populations also vary in their relative leg length and trunk and appendage length, and that impacts BMI. So if you have longer legs, your BMI at the same weight is going to be different. And there's population variation in that. So the way we've tried to deal with that is we put height into some of the models to try to account for that. We don't have, it would be great if we had something like sitting height, and then we could really get at trunk length. And we don't have that. And there's been a few smaller studies that put people into a DEXA machine that suggest that that's not driving the population level differences. But that's a possibility. It's harder to see how it would account for something when we look at more focused ethno-linguistic groups who probably have a very similar weight, leg length, etc., and we still see some differences. But that's a potential problem here, which is the different ratio of leg length to trunk length. Yeah. Now again, there's been a few studies. There's been one particularly done in Ethiopia where they did measure leg length and height, and they actually put people in a DEXA machine and look at fat mass and lean mass. And even when you account for differences in body leg length, etc., the racial and ethnic differences don't disappear in fat mass at a level of BMI, which is interesting and sort of encouraging. But it would be great if the DHS measured a few more things. And waist circumference would be another, because people carry fat in different ways too, which also has implications for cardiometabolic disease, which again we can't get at with these kinds of data. Yeah, but it's something we're thinking a lot, and I can tell you that anybody who reviews these papers thinks along those lines too, because it has the possibility. Leg length would have to vary in a very systematic way with some of the other things we've measured for that to draw this. But once you start talking about genetic ancestry, then it's really possible all these things could covary. Yeah, so it's a great question, and I wish I could say we can control for that. We can pull out height, and it doesn't seem to affect our results here. But but that's a really good question. Yeah, thank you. All right, well, thanks everyone for listening.
Let's go to EJ.